Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, what are the representative elements of the periodic table? Okay, so the representative elements you can think of these elements as like the main group elements. In the S and P blocks. With the exception of the noble gases. Okay, so these elements have completely filled inner orbitals. And incomplete outer orbitals. Okay, so some examples are like your alkali metals, lithium, or like your alkaline earth metals, like beryllium, and even like your halogens, like chlorine and fluorine. And bromine and sodium. Okay, so let's see what the junior tutor said. Some elements from the S blocks and P blocks are called representative elements because the outer shells are not completely filled with electrons and will achieve inert gas configuration by losing, gaining, and or sharing electrons. So in this diagram they have here, the representative elements is the elements shaded in gray. The middle are the the middle transition elements. And lastly, the last two rows are the lanthanide and actinide series, and then in the red are your noble gases. So group 1 elements are also called alkali metals and are metallic with one valence electron. The elements are soft solids. They have low densities as compared to heavy metals, good conductors of heat or electricity, and they have low melting and boiling points as compared to heavy metals. So group 1 metals are very reactive. So this is like lithium and sodium. And for group 2 elements, alkaline metals, they have 2 valence electrons. They're soft, good conductors of electricity, and are reactive with reactivity increasing as you go down the group. Group 3 elements have 3 valence electrons, so their metals are soft, have a lower melting point and boiling point, and also good conductors. So this is like aluminum. And then group 4 have 4 valence electrons and semiconductors of electricity. So this is like carbon. Group 5 have 5 valence electrons, and their physical properties change from nonmetal to metallic properties. So this is like phosphorus. And then group 6 consists of nonmetals, metalloids, and metals with 6 valence electrons. And the properties, they range, so that's why they have different types. So for example, like oxygen and sulfur. And then for group 7, these are the halogens. Melting and boiling point increases as you go down the group, and reactivity also decreases as you go down the group. So then this is like our fluorine, chlorine, and bromine. So this solution is correct. Okay, so question 2. Ethane, ethene, and ethine each consists of 2 carbon atoms but a different number of hydrogen atoms. Which molecule are each of the Lewis structures? Okay, which molecule are each of the Lewis structures and electron and molecular geometry pair associated with? Note that the geometries given correspond to the geometries associated with the carbon atoms only. So here they just have, like it's one of those interactive questions where if you have ethane, ethene, or ethine, you kind of label which of these electron and molecular geometry pairs associates with that structure and also with that chemical compound. So let's start off with ethane. Ethane has the structure H2H6, and even just by looking at the suffix of ethane, we know that it only contains single bonds. So it will have the 2 carbons single bonded together, and then all around are all of the hydrogens. Okay, so this is the structure of ethane, just all with single bonded hydrogens. And now if we analyze this Lewis structure, we, judging by the central carbon atoms, we see that there are 0 lone pairs. And we have 4 bonded atoms. Okay, so to help us answer this question, we can look up a helpful Vesper Theory table. So I like to use this one because it has all the different columns that have hybridization and bond angles. And if we pair up the structure that has 0 lone pairs and 4 bonded atoms, we get this tetrahedral molecular shape and electron geometry. I'm just going to write that down over here. So when our central atom contains no lone pairs, then its molecular shape and electron geometry will be the same. So in the case of the 4 bonded atoms and 0 lone pairs, tetrahedral is the molecular shape. And the electron geometry. And the type of hybridization is called sp3 hybridization. Okay, so now let's look at ethene. And its chemical formula is C2H4. So again, if we look at its name, the prefix eth tells us there's 2 carbons in the chain, and the fact that it ends in ene means that there is a double bond in between the 2 carbons. So we can say that its Lewis structure contains the carbon double bonded with the other carbon, and then we just fill in all the bonds, the remaining bonds with hydrogens. So now we have the structure for ethene. So again, let's look at the number of lone pairs and the bonded atoms. So again, this central atom contains 0 lone pairs, but this time there are only 3 bonded atoms to our carbon atom. So each carbon is bonded with 2 hydrogens and the other carbon. So now if we use the Vesper table to find out the type of shape we have, 3 bonded atoms and 0 lone pairs corresponds to a trigonal planar molecular shape and electron geometry. So I'm just going to write trigonal planar. And I'll just put in brackets for both molecular shape and electron geometry. And this time we have sp2 hybridization. Okay, so lastly we have Ethine. C2H2. So this ends in ine. So this means that there is a triple bond in between our 2 carbons. And since carbon wants 4 bonds in total, I'm just going to draw the 1 hydrogen attached to each carbon. And now we have the Lewis structure for ethine. So if we analyze the Lewis structure, there are still 0 lone pairs for carbon, and this time there are only 2 bonded atoms. And according to our Vesper Theory table, when we have 2 bonded atoms and 0 lone pairs, we have a linear molecular shape and also a linear electron geometry. So I'm just going to say linear for both. And this time we have sp hybridization. Okay, so these are our 3 compounds, and I believe we answered all the questions, all the sub-questions in this question. Let's see what the junior tutor said. Obtaining the steric number of the carbon atom would be helpful to determine the geometry of the given compounds, where Sn is equal to the lone pair plus the bonds around the atom. So, yep, so here they just define it. Sn steric number. Lp is the number of lone electron pairs around the atom, and B is the number of bonds around the atom. So this is a different approach, but it's basically doing the same thing. The table below shows the corresponding geometries for a given steric number. So when you have a steric number of 2, you have linear, and when you have 0 lone pairs, it's going to be the same. 3 is trigonal planar, 4 is tetrahedral. The Lewis structure for ethane is shown below. Okay, so they have the same structure and also got tetrahedral. For ethene, they have the double bond and they have trigonal planar. And then for ethine, they have the triple bond and a linear electron geometry and molecular geometry. So this solution is correct. I'm also going to say we can use the Vesper Theory table to solve the answer. Sometimes this the Vesper Theory table is given in the quiz or in the test, so it's also good to know how to use it because it gives off a lot of information. Okay, so question number 3. What is the Lewis structure of ammonium chloride? Okay, so when we write out the Lewis structure, we first want to calculate the total number of valence electrons. Okay, so for nitrogen, nitrogen has 5 valence electrons. Hydrogen has 1, and we have 2 hydrogen atoms in this compound, so we multiply this by 2. And chlorine has 7 valence electrons. Okay, so if we add these all up, we should get 14 valence electrons in total in our structure. So now let's try to draw out the skeletal structure. We'll have nitrogen as our central atom, and then I'm just going to draw down single bonds to my 2 hydrogens and to my chlorine. So now that we have the skeletal structure, I can show all the lone pairs on my terminal atoms. So in the case of hydrogen, hydrogen will have no lone pairs since it only has 1 valence electron, and that is participating in the single bond. So it has no more electrons, so that's why hydrogen will never have any lone pairs on it. In the case of chlorine, chlorine will have 6 valence electrons. And now I like to count out how many electrons I've drawn so far. So each bond contains 2 bonding electrons, and my chlorine has the 6, so we only have 12 written down so far. So for the remaining 2 electrons, I'm going to put them on my central nitrogen atom. Okay, so we have the Lewis structure for ammonium chloride. So now let's see what the junior tutor said. Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes even radicals. It contains some trial and error, so there are some guides and rules in following it. So this is a step-by-step guide, so it's pretty much what we did. We determined the central atom, which was nitrogen, logically arranged the atoms. So if you know that this atom is able to form multiple bonds, then it's helpful to know that it would probably be the central atom. And also, usually the least electronegative, with the exception of hydrogen, is typically the central atom as well. Connect the atoms and then check the rules below are followed. If not, make necessary adjustments. Redraw the entire molecule if needed. So hopefully you don't get to that step. But now they have the rules. Make sure atoms that follow the octet state strictly have 8 valence electrons. Minimize formal charges. More electronegative atoms are given the negative formal charge if applicable. And make sure the sum of the formal charges match the charge of the compound. So we don't have a charge in our compound, so that doesn't pertain to us. And now they have their example. And they got the same Lewis structure I did as well. And they also have the equation for formal charge, which is helpful. But if we were to calculate it for all of our atoms, we should get a formal charge of 0 for all of them. So the solution is correct. Okay, so question number 4. What is the Lewis structure for the acetate ion? So it doesn't really show in the question, but the acetate ion has a -1 charge. So I'm just going to add that in. Okay, so first let's find the total number of valence electrons. So this will help us in drawing out the Lewis structure for the ion. So in the case of carbon, carbon has 4 valence electrons, and there are 2 carbon atoms, so we multiply this by 2. Hydrogen has 1 valence electron, and there are 3 hydrogen atoms, so we multiply this by 3. And lastly, oxygen has 6 valence electrons, and we just multiply that by 2. Also, the overall charge of this ion has a -1 charge, so we are going to add an additional electron to our count, and we should end up getting a total number of 24 valence electrons. Okay, so now let's try to draw out our structure. We'll have our 2 carbon atoms single bonded together, and one of them will contain the 3 hydrogens, just single bonded. And then the other one will contain the 2 oxygen atoms, but notice that it doesn't have a full octet yet, so I'm just going to make one of these oxygens double bonded, and then I'll fill in all the lone pairs on the oxygen as well. And then from here, we can count out all the electrons we've drawn so far to see if it matches our total valence electron count, which is 24. So each bond contains 2 electrons. So we have 4, 7 bonds. Okay, so now I counted it all out and we have 24. So this is the following Lewis structure for the acetate ion. But notice that one of the oxygens is single bonded and the other is double bonded. So let's calculate the formal charge just for all the atoms to see if everything lines up, since the sum of our formal charges should equal the overall charge of the ion. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so let's calculate the formal charge of all of our atoms. Let's do hydrogen first. Hydrogen has 1 valence electron. There are no lone pairs on hydrogen, so the number of non-bonding electrons is just 0. And there's only a single bond to the hydrogen, so there are 2 bonding electrons in total, divided by 2. So 1 minus 1 is just 0. For our carbon, let me just put as a subscript carbon. I'll put CH3 just so that we know that it's the first carbon. There are 4 valence electrons and no lone pairs. And there are 4 bonds to this carbon. So 8/2. So this carbon also has a 0 formal charge. For the carbon that has the 2 oxygens, it still has 4 valence electrons, 0 non-bonding electrons, and there are still the 4 bonds attached. So this carbon is the same and has a neutral formal charge. And for the double bonded oxygen, so I'll put O double. Oxygen has 6 valence electrons. This oxygen has 4 non-bonding electrons. And it's the double bonded oxygen, so there are 4 bonding electrons in total divided by 2. So 6 minus 4 minus 2 is 0. And then lastly, for our single bonded oxygen, there are 6 valence electrons. There are 6 non-bonding electrons. And there's only the 1 single bond. So we have 2 bonding electrons divided by 2. So this oxygen is the one that will contain the -1 charge. So I'm just going to add that to our structure. So now we have the final Lewis structure for the acetate ion. So let's see what the junior tutor said. A Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. So you can see they drew out their skeletal structure, made one of the carbons or one of the oxygens have the double bond, and then they added in all of the lone pairs. So now they can calculate the formal charge. So if we do the calculation, all the atoms have a 0 formal charge except for the right oxygen, which has a -1 formal charge. Yep. So this solution is correct. Okay, so question number 5. Choose the wrong statement about intermolecular forces. So for A, the attractions due to the induced dipoles and instantaneous dipole results in London dispersion forces. Okay, so A is actually correct. So London dispersion forces are caused because of this temporary attraction when the dipoles are induced, and it actually takes place in all molecules. So let's look at B. The weakest force of attraction among the intermolecular forces is van der Waals forces. So this is true as well. C. Dipole-dipole attractions are seen in polar molecules. So this is true. So let's have an example of dipole-dipole attractions. So let's say we had a water molecule. So this is the structure of water. It's H2O, and it has a bent molecular shape as well. And this is because of the lone pairs on our oxygen. So it kind of has this bent shape. Also, oxygen is much more electronegative compared to hydrogen. So we can draw a dipole moment going towards the direction of the oxygen. So this causes a partially negative charge for our molecule and a partially positive side of our molecule as well. And when we have like this polar molecule that has a partially negative and partially positive side, it can attract a different polar molecule that also has a partially negative and partially positive side. And this is known as dipole-dipole interactions. So here I'll draw another water molecule. That. And this can occur with all polar molecules, so that's why when we try to figure out if a substance can dissolve in another substance, we use the term like dissolves like. So polar molecules can dissolve other polar molecules, and non-polar molecules can dissolve non-polar molecules. So now let's look at D. Hydrogen bond is not an intermolecular force, attractive force, in which hydrogen atom bonds to electronegative atoms of same or different molecules. So this is our false answer. So hydrogen bond is an intermolecular attractive force. And I can show how hydrogen bonds occur. So this is again, that partially positive hydrogen can be attracted to the partially negative oxygen of a different polar molecule. And that's how like water molecules like stick together because of this attractive force. So it's important that the hydrogen needs to be bonded to another electronegative atom in order to have that kind of force. So like when hydrogen is bonded to chlorine, again, we'll have a net dipole moment towards the chlorine atom since it's much more electronegative. This hydrogen will be partially positive, the chlorine will be partially negative. And if we had another atom of HCl, then we get hydrogen bonding as well. Okay, so the answer is D. This is the wrong statement about intermolecular forces. So the junior tutor said that A is correct. London dispersion forces are temporary attractive forces that occur when the electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. B is correct. Van der Waals forces are indeed the weakest of intermolecular forces and exist between all types of molecules. C is correct. Dipole-dipole attractions are indeed seen in polar molecules, wherein the attractive forces occur between positive end of one polar molecule and the negative end of another. This occurs because of the uneven distribution of electrons within the molecule. Finally, D is wrong. A hydrogen bond is an intermolecular force of attraction that results from the attractive force between a hydrogen atom covalently bonded to a very electronegative atom, such as nitrogen, oxygen, or fluorine. Yep. So this solution is correct. Okay, so question number 6 is to draw the Lewis structure for sulfur trioxide. Include all resonance structures. Okay, so when drawing out the Lewis structure, we need to first find out the total number of valence electrons in our molecule. So sulfur contains 6 valence electrons, and oxygen also contains 6, and there are 3 oxygen atoms, so we multiply this by 3, and we end up with a total of 24 valence electrons. So now let's draw sulfur as our central atom. And then I'll just draw 3 bonds to oxygen, like so. And all of the oxygen atoms will be double bonded. So this is because sulfur is one of those exceptions where it is able to have more than 8 electrons in its valence shell. And in the case of oxygen, all the oxygen atoms will prefer to have the double bond so that they can have a full octet as well. So now let's count out all the electrons in the structure to make sure that we have 24. So each bond contains 2 bonding electrons, and each oxygen has the 4 lone pairs. So we have 24 shown in this molecule. So now let's try to calculate formal charges. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So all of our oxygens are the same. They have 6 valence electrons, 4 non-bonding electrons. So these are in the form of the lone pairs. And then each of them have a double bond. So we have 4 bonding electrons in total divided by 2. So all of the oxygens have a 0 formal charge. So now let's do the same thing for the sulfur. Sulfur has 6 valence electrons, and there are 0 non-bonding electrons. And for bonding electrons, there are 6 bonds, so we have 12 bonding electrons in total divided by 2. So the sulfur also has a formal charge of 0. So we know that the structure is correct. And since there are no, since all the oxygens are the same, this is the only resonance structure for this molecule. So now let's see what the junior tutor said. The molecule consists of 1 sulfur, 3 oxygens. Both have 6 valence electrons. So if you count out all of the electrons that the junior tutor said, let me double check. You end up with 26 when we should only be having 24 valence electrons. And also, these oxygens will have a negative charge. Yeah, so all the oxygen, these 2 oxygens that are single bonded will have a negative charge. And if we calculated it for the sulfur, it would be 0. Yeah, it would be 6 minus 2 minus 4. But since the sulfur would be 0 and the 2 oxygens would have a negative 1 charge, then the overall structure would have an overall negative 2 charge. But for our question, the molecule should only be neutral. So this solution is incorrect. Okay, so I said that this solution is incorrect. The central sulfur atom will have 3 double bonded oxygens. Should have 3 double bonded oxygens. The structures drawn will have a net. The structures shown Structures shown have a net charge of -2, and the total electrons are 26 when it should only have 24 electrons. The central atom should have 3 bonded oxygens for the correct Lewis structure. Okay, so question number 7. What is the Lewis structure for CO3 2-, which is our carbonate ion? So first, let's calculate the total number of valence electrons. So carbon has 4 valence electrons. Oxygen has 6. And there are 3 oxygen atoms, so we multiply that by 3. And also the overall charge of this ion is -2. So we're going to add an additional 2 electrons to our count. And you should end up with a total of 24 valence electrons. So now let's draw carbon as our central atom. And if we were to draw 3 single bonded oxygens, you'll notice that the carbon doesn't have a full octet yet. So I'm going to make one of them have a double bond. So now let's fill in all of the lone pairs on our oxygens and count out how many electrons I've drawn in the structure. So each bond contains 2 bonding electrons, and we end up with a total of 24 electrons for this structure. So it looks correct, but to double check, we can calculate the formal charge of each of the atoms just to see if the sum of the formal charges is going to equal -2, since the overall ion has a -2 charge. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so first let's calculate the formal charge of our carbon atom. So carbon has 4 valence electrons. There are no lone pairs on the carbon, so we just write 0 for non-bonding. And there are 4 bonds to the carbon, so there are 8 bonded electrons in total, divided by 2. So the carbon has a 0 formal charge. So now let's calculate the formal charge of our oxygen that is double bonded. Oxygen has 6 valence electrons, and this double bonded oxygen has 4 non-bonding electrons. And it has the double bond, so there are 4 bonding electrons in total, divided by 2. So our double bonded oxygen has a formal charge of 0. And now let's calculate the formal charge of our 2 single bonded oxygens. So they have 6 valence electrons and 6 non-bonding electrons. And they both have the single bond. So there are 2 bonding electrons divided by 2. So 6 minus 6 minus 1 is -1. So we can show that these 2 oxygens will have a formal charge of -1. And again, if we added up the sum but if we added up the formal charges, we have an overall charge of -2 for this ion. So this is expected. So we know that this is the correct Lewis structure for the carbonate ion. So the junior tutor said that a Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. So they have a nice step-by-step guide. Determine the central atom, logically arrange them, connect them, and then check if the following rules are followed. Not make necessary adjustments, and then you might need to redraw the entire molecule, but hopefully you can just try to get it right the first time. And for the rules, make sure that the atoms that follow the octet state strictly have 8 electrons. So this is like carbon, it needs to have 8 valence electrons. You can't form like 5 bonds with carbon. Rule number 2, minimize formal charges of the atoms if possible. So we knew we couldn't really do that with ours because it needs to have a charge of -2. More electronegative atoms are given the more negative formal charge if applicable. So we can double check with ours. Oxygen is more electronegative than the carbon, so they also carry the more negative formal charge, which is good. Make sure the sum of the formal charges match the charge of the compound. So in our case, they do. And I think now the junior tutor shows all the steps to their answer. Okay, they have the equation for formal charge. And they have the final correct Lewis structure. So this solution is correct. Okay, so question number 8 is a 2-part question. Both PCl3 and PCl5 are stable compounds. Draw Lewis structures for these 2 compounds. And part B, nitrogen trichloride is a known compound, but all attempts to synthesize have failed. Draw Lewis structures for and a hypothetical nitrogen pentachloride and explain why this is an unlikely structure. Okay, so first let's do part A, starting with phosphorus trichloride. So first let's calculate the total number of valence electrons for this compound. Phosphorus contains 5 valence electrons, and chlorine contains 7. And there are 3 chlorine atoms, so we multiply this by 3. And if we added it all up, we get a total of 26 valence electrons. So now let's show phosphorus as our central atom with the 3 single bonded chlorines attached. And I'll also show all of the lone pairs on my chlorines as well. And if we count out all the electrons in this structure, we only have 24 out of the 23 out of the 26. If each bond has 2 bonded electrons, so we just need to have 2 more electrons and they can go on our central phosphorus atom. Okay, so this is the structure for PCl3. So now let's try to do the structure for PCl5. It's going to have a total valence electrons with phosphorus 5 plus the chlorine, which is 7 times 5 this time. So 35 plus 5, so that gives us 40 valence electrons. So phosphorus will be our central atom. And then I'm just going to have all of the single bonded chlorines. And show all of their lone pairs. So phosphorus is one of the exceptions to the octet rule in which it's able to form more than 4 bonds. And if we count out all the valence electrons I've drawn so far, we should have 40 in our structure. Yep, so 8 times 5. So that is part A of this question. So now for part B, we need to draw Lewis structures for and a hypothetical NCl5. So first let's show the Lewis structure of the nitrogen trichloride. And let's calculate its total valence electrons. Nitrogen has 5, chlorine has 7 times 3, so 26 electrons in total. And similarly with our PCl3, I'll draw in all of the lone pairs on the chlorine, and our nitrogen should have a lone pair as well to get 26 electrons. So now let's try to draw that hypothetical nitrogen pentachloride. And we'll calculate its total valence electrons first. This also gives us 40. And now let's attempt to draw this hypothetical structure that will probably look like the PCl5 with all the chlorines all around it like this. Kind of going into my equation there. You kind of get the gist. So you get a structure that kind of looks like this. So this is incorrect. And I'll try to fit an explanation why up here. So if we write out the electron configuration of nitrogen, it is 1s2, 2s2, 2p3. So to form nitrogen pentachloride, we need 5 unpaired electrons, and they are required. Nitrogen only has 3 that are able to bond, I should say. Since the electrons in the s orbitals won't participate in the bonding. So the reason why phosphorus is able to form the 5 bonds is because it has another d orbital, and it's able to have multiple bonds. So this nitrogen has no expanded d orbital. There is no expanded d orbital. Okay, so let's see what the junior tutor said. They have the Lewis structures for PCl3, PCl5. Oh. Looks like they didn't tackle the second part of the question. Okay, so I said for part B, NCl5 is an unlikely structure since to form NCl5, 5 unpaired electrons are required and nitrogen only has 3. And then I just tried to draw its electron configuration. Nitrogen has no expanded d orbital unlike phosphorus. I think that was like the main part of the question that should have an answer, so I'm just going to say this solution is incorrect. Okay, so question number 9 is just to calculate the molar mass of potassium chloride, which is KCl. So to find the molar mass of potassium chloride, we'd need to find the individual masses of both potassium and chlorine. So these values are just found on your periodic table. And to find potassium chloride, we just need to sum up the molar mass of potassium plus the molar mass of chlorine. So potassium has a molar mass of 39.1. Again, you just need to find this value on your periodic table. It might be in units of atomic mass units, but now it's just the same value as your molar mass. And chlorine has a molar mass of 35.5 grams per mole. So if we added these values up, you get 74.6 as your molar mass, and therefore this is option A. Okay, so the junior tutor said the same thing. Molar mass is equal to the atomic mass of potassium plus atomic mass of chlorine. And they also got 74.6. So the solution is correct. Okay, so question number 10. How many grams of calcium chloride are needed to prepare 5.17 liters of 0.5 mole per liter calcium chloride solution? So let's write down everything that's given. We know the molar mass of calcium chloride, which is equal to 111.0 grams per mole. We need to have a volume equal to 5.17 liters. And we know that we need to prepare a concentration of 0.5. Concentration of 0.5 molar. So this is the same thing as moles per liter, so I'm just going to write it as moles per liter just so that we can see the units. And we're looking for the grams, so the mass is equal to grams. Okay, so we wrote down everything that's given, so let's try to break it up into the different steps. So step 1 is to find your number of moles needed in the solution. So if we recall the equation for concentration, concentration is equal to the number of moles divided by the volume. So if we rearrange this equation, we can solve for the number of moles just by multiplying concentration and volume. So for our question, the desired concentration is 0.5 moles per liter, and the volume is 5.17 liters. So if we multiply the two, our liters will cancel out, and we're left with our value that is in moles. So you should end up getting 2.585 moles. Okay, so the second part of the answer is to now solve for mass. So if we remember that to find the number of moles, you do the mass divided by the molar mass. Now we can rearrange this equation and solve for mass by multiplying the number of moles that we found in the previous step by the molar mass of calcium chloride. So the mass is equal to 2.585 moles times our molar mass, which was the 111 grams per mole. So now our moles will cancel out and we're left with our answer in grams, which should be around 286, I think my notes say. 0.935. Let me double check that. 2.585 times 111, 286.935. Yep. Okay, so this is the number of grams needed to prepare 5.17 liters of 0.5 calcium chloride solution. And it is option number B in the multiple choice. So therefore B. So let's see what the junior tutor said. They wrote down everything that was given. So I think they meant to say 111 instead of just 11. Volume and concentration. First, they multiplied concentration and volume to get 2.585. And they multiplied number of moles by the molar mass, and they also got around 287. So this solution is correct. Okay, so question number 11. What is the molecular geometry of carbon dioxide? CO2. So to help answer this question, we need to write the Lewis structure. So first, let's calculate the total valence electrons for this molecule. Carbon has 4, and oxygen has 6, and we multiply this by 2 since there are 2 oxygen atoms, and you should end up getting 16 valence electrons. So now let's draw carbon as our central atom. And if we were to just draw 2 single bonded oxygens, you'll notice that carbon doesn't have a full octet yet. So these will both be double bonded. And then I'll just draw in my lone pairs on the oxygens. And if we count out all the electrons in this structure, each bond contains 2 bonding electrons. So we have 8 plus 8. So we have our 16 valence electrons. So this is the correct Lewis structure. So now let's analyze it to find out its molecular geometry. So for this structure, we base the molecular geometry on the central atom, which is carbon. So carbon contains 0 lone pairs. And there are also 2 bonded atoms. So we need to use our Vesper table to figure out its molecular geometry. So here, when we have 2 bonded atoms and 0 lone pairs, we have a linear molecular shape and also a linear electron geometry. I'm just going to write linear. The carbon is sp hybridized, and the bond angle will be 180 degrees. So you can kind of tell this is 180 degrees. So our answer is B. So our junior tutor said to find the molecular geometry of carbon dioxide, we need to obtain its Lewis structure. So they counted out their valence electrons to get 16. And then they drew out the correct structure, which is linear. So this solution is correct. Okay, so question number 12. What are the possible Lewis structures for this SCN- ion? What is the formal charge of each atom in the structure? What is the best Lewis structure? So first, let's calculate total number of valence electrons for this ion. Sulfur has 6, carbon has 4, nitrogen has 5, and the overall charge of the ion is -1. So we're going to add an additional electron to our count, and we should end up with 16 valence electrons for this structure. So carbon is the least electronegative, so it's going to be our central atom. And then let's see all the different structures we can obtain. So you could have a triple bonded sulfur and a single bonded nitrogen. And I'm going to write the equation for formal charge up here. So formal charge is equal to the number of valence electrons minus the number of non-bonded electrons. So these are all the lone pairs, or the electrons in the lone pairs, minus the number of bonded electrons divided by 2. Okay, so let's calculate the formal charge of this. For the sulfur, sulfur has 6 valence electrons. It has 2 non-bonding electrons. And there are 3 bonds to the sulfur, so there are 6 divided by 2. So 6 minus 2 minus 3 gives us +1. So we know that this sulfur contains +1 formal charge. And the carbon will have 4 valence electrons minus 0 non-bonded electrons minus 8 bonded electrons divided by 2, which is 0. And for the nitrogen, there are 5 valence electrons, 6 non-bonded electrons, and 2 divided by 2. So 5 minus 6 minus 1 is -2. So this nitrogen has a -2 formal charge, and the sulfur has a +1 charge, so that's why the overall charge of this ion is -1. So let's try to draw a different resonance structure. Let me try to color code it. So let's see if we have double bonded sulfur and a double bonded nitrogen. So I'm only going to do the formal charge for sulfur and nitrogen, since I already know for carbon, it's just going to be 0. So for sulfur, there are 6 valence electrons, 4 non-bonded electrons, and 4 divided by 2 bonded electrons. So 6 minus 4 minus 2 is 0. And the formal charge of nitrogen is 5 minus 4 divided by 2. So 5 minus 4 minus 2 is -1. So we know the nitrogen just has that -1 charge. So this is why The overall ion has the -1 charge. So now let's try to fit in a last resonance structure. And let's see what happens if the sulfur is now single bonded to the carbon and the nitrogen is triple bonded. The sulfur has 6 valence electrons. There are 6 non-bonding electrons and only a single bond. So 6 minus 6 minus 1 is -1. And for the nitrogen, we have 5 minus 2 minus 6 over 2. So 5 minus 2 minus 3 is just 0. So this is if our sulfur contains the -1 charge. Okay, so these are all of the different resonance structures. And typically to find the best Lewis structure, we want to have the least number of formal charges in the structure. So we can already rule out our first option. And we want the formal charge to go to the negative formal charge to go to the more electronegative atom. So let's compare the electronegativity values of both sulfur and nitrogen. So nitrogen has an electronegativity of around like 3.0, and sulfur has an electronegativity of 2.5. So therefore the middle resonance structure would be the best one, since the nitrogen is the one that has the negative formal charge. Okay, so let's see what the junior tutor said. They explained a Lewis dot structure and had all the different steps and the rules. And you can see there are 3 different options. And all of the formal charges in a helpful table. Okay, so it's in the same order as mine, so that's good. So, yep. Based on their formal charges, the middle and right structures are considered better than the left because they have fewer and smaller formal charges. Based our decision solely on the rule, then the middle structure is more preferable because the negative charge is on the more electronegative atom. Yep. So this solution is correct. Okay, so question number 13. What is the electron configuration of a magnesium ion? I think they mean Mg2+, since an ion should have like a charge. So to answer this question, we need to divide our periodic table into the different orbitals, s, p, d, and f. And then starting from hydrogen, we move left to right across the periodic table until we get to our desired element, which is magnesium, found here, atomic number 12. So then let's just write the electron configuration of ground state magnesium first. So the electron configuration would be 1s2, 2s2, 2p6, which corresponds to the 6 electrons in this orbital, and then finally 3s2. So now when we want to write the electron configuration of a magnesium ion, which was probably Mg2+, this means that it lost 2 electrons, so the 2 electrons being the ones in the s2 orbital. So we can write a new electron configuration, which is 1s2, 2s2, 2p6. And the junior tutor looks like they said the same thing. The overall description of the placement of electrons around the nucleus: magnesium has atomic number of 12. Its ionic form is Mg2+. So this solution is correct. Okay, so question number 14. What is the molar mass of ammonia, which is NH3? So to find the molar mass of ammonia, we need to know the different atomic masses for both nitrogen and hydrogen, and we just find these values on the periodic table. So the final answer will be the sum of the molar mass of nitrogen and 3 times the molar mass of hydrogen, since there are 3 hydrogens in ammonia. So the molar mass of nitrogen is 4.00 grams per mole, and the molar mass of hydrogen is 1.01 grams per mole. So if we add these up, we get around like 17.03 grams per mole, which is option letter C in the question. So the junior tutor said, to obtain the molar mass, consider every atom that makes up ammonia and calculate their total atomic masses. So they did 14 plus 3.03, and they also got 17. So this solution is correct. Question 15 just asks, what is a conjugate base? So a conjugate base is formed when an acid donates a proton, which is just the same as H+. So let's have an example where we have an acid such as hydrochloric acid. So this is our acid, which is the proton donor. Plus, let's say we had water acting as our base, which is the proton acceptor. And when the reaction takes place, the acid will donate its proton to the H2O to get H3O+, which is known as our conjugate acid, and Cl-, which is our conjugate base. So this is the one that was formed when the hydrochloric acid donated its proton and became Cl-. The junior tutor said that the conjugate base is a product of the reaction when acid donates its proton and has a negative charge as shown in the reaction below. And then they just labeled it. The A- in this case would be the conjugate base. So this solution is correct. I think we have time for one more quick question. Number 16. What is the equation for perchloric acid dissolving in water? So when we have perchloric acid, it's HClO4. And it's a strong acid, so this means it will fully dissociate in water. Let's try to show out the reaction that takes place. If we had the perchloric acid plus water I'll first show how the perchloric acid will dissociate. So we'll have the H plus ClO4 minus plus the water. And now we can also show the resulting reaction where the proton will react with the water and we end up with H3O plus, which is the hydronium ion, plus ClO4 minus. Okay, so the junior tutor said that there are many theories that describe the properties of acids and bases. One of these is Arrhenius Theory. According to this theory, an acid is a substance that releases a proton or hydrogen ions. On the other hand, bases are substances that release hydroxide ions in the solution. When an acid is dissolved in water, the acid will be dissociated into H+ and its conjugate base. Applying this to the perchloric acid, we can write the equation for its dissolution as shown below. Okay, so they have the H+ and then they have a chlorine ion, but this is actually these are the ions that are formed when we just have normal hydrochloric acid. So this solution is actually incorrect. And then I'll just write out my two reactions. I'll just write the final one. H3O plus ClO4 minus. Okay, so those are all of the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you liked today's video, you can give it a like and a comment, and don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.